You mean the difference between the first encoding and second encoding? That depends on your volume fraction. The larger the volume fraction, the bigger the difference you will have.
Okay. So my name is Xiaoming Lin. I'm actually former postdoc for Heinrich Jaeger many years ago. So, how many years? 15 years ago, roughly. So now I work at the. So if you know me personally, you're probably pretty old. Stating this JFI too long. So I work at about 45 minutes away at Argonne National Lab, and so the talk I'm going to give it to you is actually essentially an infomercial. So how many people actually been to Argonne? Oh, quite a few. Good. So this is actually the facility at Argonne National Lab, connected with the synchrotron facility, APS. And so this Center for Nanoscale Material is this building, which is connected directly to the ring. And this large square building is more conventional lab space, as well as here's more office space. Here's more lab space, including the front end of that lab space is a clean room facility. And this long building in the end actually is the secondary building of the CNM, is now hosted several high-end scanning probe microscopy as well. So the center is actually it's a user facility, so that's why I'm saying I'm doing advertisement for the center. We have about 500 users per year, and from many different states, and 49% is from university, and then the rest of them are from either the industry and as well as National Lab itself. And we have about 300 publications per year. That's including all the users' publication as well as the staff publication. And the user access of the facility is actually through user proposal. So you write a proposal. This proposal gets evaluated by a peer review committee. And if your score is really meet the cutoff line, and then you get accepted, then you can access our center. So there are 5 different nano centers around the country. Argonne is one. Then we have one on the West Coast, Molecular Foundry. SINT is Los Alamos and Sandia National Lab facility. And then there's one at Oak Ridge, and then there's one at Brookhaven. But of course, right now, the Trump's budget is going to cut the SINT as well as Brookhaven. So we hope this doesn't happen, but we just have to cross our finger for it. So our center is actually, when we go out, we always tell people that the access to this facility is for free. And there are several different research capability here at the center. So if you are not familiar with them, you are welcome to really look at our website or even come out to a visit. And so one of the crown jewel of our center is this hot X-ray nanoprobe. And so this is actually one of the first X-ray nanoprobe in the world. Since this was built in 2007, then following years, in the last 10 years, there are several X-ray nanoprobe beamlines around the world, including another one actually in APS that is more focused on the biological systems. So they have a cryo capability, our center, our beamline doesn't have. And we of course have this high-end class 100 clean room facility with a lot of electron lithography, beam lithography system, focused ion beams, and a system like that. We have capability to synthesize nanoparticles, and we have a microscopy center, electron microscopy center. Initially, it's an independent facility. Now it's merging with Center for Nanoscale Materials. And we have a variable temperature, high magnetic field, AFM, STM. And then here have a pump probe and optical spectroscopies. And we also have a very strong theory group, a modeling group now. Now actually it's one of the strongest group in our center because half of the second floors postdoc, they have so many fundings that a postdoc actually taking up half of the second floor space in our center. So the theory modeling group is really a strong point now in our center. We have, so these facility users scattered all over the places, including all sorts of all around the country, as well as somewhere in Europe and in China. Actually, I have a group that collaborate with me from China right now, send students over here, all the way to here in the facility. And the PI bought a house in Naperville, so put all the students in, and then they come. So which is a little bit extreme, but I'm really happy to just happen for our facility. So there are, research-wise, there were 5 different groups right now. The groups sometimes change a little bit, but more or less stay the same. The group I'm in specifically is a quantum energy material. I specifically myself don't do quantum material, but sort of related to the energy material a little bit. And then there's a group in nanophotonics, biofunctional structures, fabrications is one aspect. Theory and electron X-ray microscopy is a different group. So I'm going to give you a little bit what they do, really, because I only know a little bit about each group. So I will give you a small fraction of the examples what they do later on. So X-ray fabrication group, of course, you are familiar with. And so one of the key person is here, which is Leo Kola, who pretty much hired at the same time when I was hired in 2002. And he originally came from Bell Lab, so that he was one of the leading electron microscopy lithography persons in Bell Lab. And so he helped lead the effort to build up the systems. Group leader is Daniel Lopez, who also, I believe, come from Bell Lab as well. So they basically now be able to fabricate some fascinating structures through lithography. And this is the Leo dressed up, pretty much covered. You can't even really see him. One example, for instance, they are able to make, this is actually schematics, but it is a microfabrication mirror that are operating in a very high frequency. So when they flip these mirrors on the chips, so they can deflect the X-ray beam comes into 2 different directions. So essentially it's a mirror chopper. So they can chop the X-ray into a very fine pulse. And that's very hard to do. And it was done by electron lithography system. So that helps a lot to do X-ray, fast pulse X-ray chemistries on the beamline. So quantum energy materials, we are looking at basically the major part of the group is looking at scanning probe microscopy. So they're looking at low temperature STM, manipulate atoms on the surface, what kind of spectroscopy in 2D materials. And one of the really a breakthrough a couple of years, probably 2 years ago now, is this graphene. It is essentially discovered at Argonne in our center, and this is made to the science magazines. And so this is actually a 2D analog of graphene, but made of boron. Okay, so that's the first thing is discovered at Argonne. And this picture here is the work that we collaborate with Heinrich here, and looking at a membrane, self-assembled membrane, ligand asymmetries on X-ray on the water-air interface. So we have our group basically we have a large amount of effort in STM effort, but also have material fabrications in 2D nanoparticles, membranes, polymer systems in this group. Theory group is actually in our center ourselves, we have on the 2nd floor, we have a high performance computing facility itself within the center. So 2100 core carbon systems, but there are different PIs that expertise in different areas. So there are people who work on electronic structural calculations. There are people doing electromagnetic molecular dynamic simulations, and there are also people doing calculation on optical related, the nanoscale optical and plasmonic phenomena. So they also have access to the ALCF, Advanced Leadership Computing Facility at Argonne, which is a supercomputer, right? And the name is called a Mirror. This is now the 5th largest, I think it's the 5th largest computer, fastest computers in the world. But they are making another one, upgrade another one. So nanophotonics and biofunctional materials, they are basically looking at optical spectroscopy And they try to looking at electronic transitions in biostructures, biomolecules. And so they have these palm probe experiments and have a very high, very fine temporal resolutions, as well as try to focus the light beam into very small space. And so they also cover a variety of energy range. So they can all the way from UV range to the middle IR range with high spatial resolutions. And electron X-ray microscopy group, as I mentioned, there's X-ray nanoprobe. So what it does is that it takes X-ray and it goes through an X-ray Fresnel zone plate and it focuses the X-ray down to a very tiny spot. Okay, the spot can be that they're working very hard to make the spot smaller as possible. And so the current spot is reasonable spot size is about 30 nanometer. In some cases, they can get to, depending on the technique, they can get stuff down to 10 to 15 nanometers. And so what they do is that they focus the X-ray, they scan the X-ray beams on the surface of your sample, and then they're looking at X-ray fluorescence. X-ray fluorescence can tell you the chemical compositions locally on that spot, right? And they can also looking at X-ray diffraction that tells you crystal structures and at that local spot, right? So what they do very well is these chemical sensitivities is very tiny amount of material. They can pick it up, right? And they can also picking up very small changes of lattice, crystal lattice structures. So it's a strain of the crystals. If there's tiny changes of that, they can pick it up very, very easily. And we're also looking at this is actually, I'm involved in this, and putting a rheometer at the X-ray beam line. So we're developing some of the X-ray, small angle X-ray scattering correlated with X-ray photon correlation spectroscopy in situ with a rheometer, something that you guys are granular physics and even people here are going to be really excited about. And the third technique it's called an SSSTM. So it's a technique that combines X-ray with the scanning probe microscopy. So essentially what that does is that you take the X-ray, go through the absorption edge of each different elements. So if you know that X-ray spectroscopy, you will know that if you go through you tune the energy of the X-ray, go through the absorption edge, then essentially you have a large absorptions, right? So you will change the electronic absorption edge of that element. So what happens is that locally the XTM is acting as an antenna to pick up the signals from the samples. So they can actually have chemical specificities locally, what kind of elements, single atom elements is corresponding to for that specific area. So finally, we have an electron microscopy center. We recently have purchased an operation corrected TEM. It's not the top of the world operation correction TEM, but it actually can do a fairly good job. And then we also have quite a few people that are specialized in this microscopy facility. We are hiring people also in this area. Now, one example you should know is that the famous example that was done at Argonne is using this X-ray nanoprobe to look at Picasso's pigments. So essentially, you can scan a very small sample of the pigment. You can find out what kind of elements of that paint is being used by Picasso's painting back there, right? So it's actually one of the best way, as far as I know, to find out the counterfeit things. Because if you are try to fabricate a new painting like that to be a counterfeit, it's a fake ones, and the paint material you use today is very different paint material used in 1800 or 1900. So that is the best way to find out what is real or what is not real of the Picasso painting. So let me, I have about 10 minutes or so I'm going to give you a few examples what sort of the science problem. I just only give you a few examples which I thought was kind of interesting examples of my colleagues are working on. Some of them I'm more familiar with, some of them which I'm less familiar with. And so this is actually a system that my colleague Jeff Guest is building. It's a 4 Kelvin ultra-high vacuum STM system. The unique system of the unique aspect of the system is actually is combined with optical systems excitations with the scanning probe. So this is actually a high numerically aperture optics, and this is where you put the sample. The STM tip is coming from the top. So essentially, what they do is they want to excite the sample with optical, from the light, and excite these samples into high energy, high excited states, and then probe these samples from electronic states by STM. So these are the things that they are home built. Everything you cannot really buy it commercially, but these are extremely difficult experiments, and because a lot of time you shine a laser on the sample expands really quickly, and this STM, one of the STM working functions is you have to maintain the distance between your tips and samples, and you have to be able to count the expansion of the sample into effect. So these are very difficult experiments. So what they have been doing recently is looking at, for instance, a 2D material, defects in the 2D material, such as tungsten diselenide monolayers, and these are the defects, actually, a group in University of Washington. What they find out that the excitations from these defect sites are extremely sharp. And so the question is why these defects is giving you that kind of extreme sharp optical signals. And also, can you actually engineer your own defect in these 2D materials? Can you understand the coupling between the defects and the electronic spin state in these systems? So this is an example of what they did. This is the STM topography. And looking at it, if you look at a defect, it's not a single atom defect, obviously. So it has several different atoms, group of atoms involved in these defects. And these are electronic structures associated with defect. So they are slightly obvious, different from the topography. And so these are the things they're looking at to understand how intrinsically the behavior of the defect sites. Another example that developed argon is this so-called super lubricity behaviors. And these are experiments and theory, both done at argon. That's actually in our center. The experimental part is what people have been trying to put in some graphenes, spray some graphenes onto a surface. So they are looking at the frictions, essentially. So what they find is that if you start to put graphene sheets on the surface, and then they sprinkle a few nanodiamond particles onto the surface. And what they find out, if they do that, especially with nanodiamond particles, they find out that the friction coefficient drops dramatically into so-called super lubricity conditions. And eventually, so they try to understand exactly what happens. And then eventually they realize that when you sliding material onto these kind of a system, you are essentially wrapping graphene layers onto these nanodiamond sheets. Okay, so once that happens, it decreases the friction force between the ball, which is you are trying to push, and the surface dramatically. And that's interesting effect that it's on its own. It's also published in Science in 2015. And so these are the mechanisms they're doing these kind of simulation. They basically find out exactly what happens in these type of systems. So these are all done at argons with simulation effort. I want to also give you a few examples of the X-ray. This is for some of you guys working with SEM, you know that if you are imaging a soft material, imaging a biological material with the SEM is very difficult. There's a charging effect goes on, you cannot really see anything, so the resolution is really low, right? So here's a technique that recently developed by Leo and Bob Winowski. So what they do is that they essentially taking a sample. Here's an example of a tooth, okay? So they got a piece of tooth from one of the staff's daughter. And so the daughter just, because we really cannot take biological samples into, collect biological samples from hospital, and safety won't allow this. But somehow we're sneaking one of the tooths from the daughters. So it works. So we put these tooths in ALD system. So it's a atomic layer deposition systems. So essentially, you evaporate a thin layer of zinc oxide, into the system. And if you do it right, the zinc oxide vapor can penetrate very deep into these two structures and coat a thin atomic layer coatings on the surface. And zinc oxide is a semiconductor, but it's also slightly conductive, right? I mean, lot more conductive than the tooth material. And so apparently it works very, very well. So you actually coat these systems very, very nicely. And a similar application way of doing it, they also did it on brain tumor, basically tumor cells, things, which also works. But the example I'm giving here is just a tooth structure. And you can see these are the tooth high-resolution SEM images, different features as you gradually zoom in. And you can, if you turn off the light, you can even see better. And so these kind of a structure, you can actually see very fine structures down to less than 100 nanometer. The bar here is a 100 nanometer structure now. So this is very difficult to achieve in a conventional SEM. But coupling with the X-ray, you can see even better. So this is a little tooth that they using a focus ion beam to mill a little bit to a certain thickness, and so this becomes a slightly pillar. And so then they take this tooth sample to the nanoprobe beamline. This is the first sample. First images is the one that they have a single shot of the image. You already can see internal cracks in these tooth structures and textures in these tooths. And but if you turn the sample, collect the multiple angle, and then reconstruct these systems, and you can see even better. So this is actually a tooth sample, a tomography, X-ray tomography image of this tooth sample, and a single slice at very small areas goes in. You can see very tiny structures down to 60 nanometers. So pores and everything you can see very, very clearly, right? So I think it was when Leo showed me this these slides in this January, I was very fascinated about this. So I told him that my daughter is actually going through that age. If you want more tools, I can collect them for you. So that's one of the things. Another thing that is the real SAX XPCS setup system that I taught you about. And so what we do is we put anti-par rheometers on the X-ray beamline, sector 8. So this X-ray beamline is specifically engineered to do a SAX and a XPCS. So the X-ray comes in and goes through these polycarbonate shear cells. We have a cuvette shear cell. And of course, we are hoping to gradually develop in different kind of geometry of shear cells to looking at this X-ray, looking at some of the different directions. So it is possible to use this setup to looking at rheology and the microstructures, right? And also measure the dynamics of these particles' motions through photon correlation spectroscopy. And this pretty much is a user facility now. We haven't really advertised it, but we hope to do some experiments ourselves first, especially with our close collaborator. But so I'm going to show you one example what we did. This is 300 nanometer glass spheres. We did this oscillative shear as well as steady shear at a large packing fractions. I believe this one is around 56 volume percentage volume fractions. So you see the shear thinning behavior as well as shear thickening behavior in these colloids. Another thing is that these colloids are homemade. So this polydispersity is really, really small. So if you don't have this control of the polydispersity, you see very, very different behavior. What happens is that if you're during oscillative shear, you see different behaviors. So you see these two-step shear thinning and shear thickening behavior. This first step of the shear thinning, shear thickening behavior, the critical stress here at number 3, is actually corresponding to the order-disorder transitions. So essentially what happens is that when you have oscillative shear, it's likely to form these highly ordered layer structures. And that dramatically decreases the viscosity. But if you have a steady shear, it bypasses this order-disorder transition completely. And so you got another type of, so the critical shear thickening at this number 5 point is not associated with order-disorder transition. So with the first time, we are able to distinguish this order-disorder transition-induced shear thickening versus other mechanism-induced shear thickening. All right. So as I mentioned, this center is also very heavily in the theory model. So I took a few slides for one of my colleagues, Subramanian. So what they're doing, for instance, a lot of working is on coarse-grained molecular dynamic simulations. And so what they're looking at, for instance, recently they're looking at water models. And so water typically in a coarse-grain, if you're doing a coarse-grain model, you really simply looking at typically they're looking at 4 different water molecules and approximate these water molecules as a bead, okay, with one single bead. We're also looking at a carbon chains using a Martini model. It's the same thing, so that you typically looking at 3 or 4 carbon atoms as a single bead. So you essentially represent a single bead and of 4 atoms, 4 or 6 atoms, right? And then you put model in at the interaction between these beads, and then you do the molecular dynamic simulation. So this is an example that in collaboration with Heinrich and my lab, and so essentially we're looking at using these coarse-grained model to looking at the nanoparticle membrane, and we are simulating how this membrane is actually the mechanical behavior of the membrane as you pour it, provide a tensile stress, and essentially calculating the stress strength curves. And we can actually find out a variety of things. We can find out how the molecular distributions is related to the hysteric behavior of some of the things we see in the mechanical properties. Now, so for instance, this is experimental data that basically shows that the Young's modulus at a high temperature gradually decrease, and then when you come back at the temperatures, what happens is that it has a hysteric behaviors. But what it really does is associated with ligand distributions around the nanoparticles. And so this we can capture with simulations. So for molecular dynamic simulation, the most important thing is this so-called force field. That's essentially depend the interaction between, interatomic interaction between the particles and beads. And so the force field is a core, right, to calculate these molecular dynamic simulations. So they're really developing new type of the force field. And for the water model, which I showed you before, typical water model does not really take into account the hydrogen bonding and especially the relative angular distribution of hydrogen bonding in these water models. So what they're doing is that they are adding another term in this force field and to taking into account the interaction and the tropic interactions of the potential distributions of this force field. And so they can calculate water compared with the traditional models they have in coarse-grained molecular dynamic simulation. So these are basically density anomaly of water. Experimental data is plotted in black points, and the new simulation data is plotted in these blue curves. They matches really, really well, and compare with a lot of models with different kind of approximation. And you can see this blue curve is really actually much more accurate to produce water behavior. And this is still the ongoing effort in their lab. I think they are almost ready, or at least partially submitted their manuscript already. So I hope at least you learn what's going on a little bit about our centers and the various research activity, in our centers. So if you're interested, of course, you can always contact me at this number, but you can also looking at our website and where we call for the user proposal and submit a user proposal through here. Okay? Any questions? Yeah. If no, word.
Well, if nobody asks, then I'll ask. You showed a chopper that you said was fast. Do you happen to know how fast that chopper is?
They're pushing these things into a femtosecond.
Femtosecond?
Yeah, something like that. But I'm not exactly sure about how fast they are. Because that's what the interesting chemistry.
Yeah, and how you said they were micro? How big are they? Like how big are the mirrors?
The mirror, I don't know, how big it is. They're very small.
Okay.
But I'm not so sure exact time scale. I mean, but they are hoping to push in femtosecond, but whether they achieve that,
Cool. Maybe close to by now, still 1 nanosecond.
Okay. The reason I ask is because
but I can find out.
yeah, I don't know if I don't know that we use that immediately, but we're always looking for fast displays for video. And one way of making a fast display is having a bunch of two-stage micrometers.
Oh.
So,
whether it's a cost-effective for industry, that's a different story.
yeah, no, that's true. But TI has a bunch of displays that are essentially micrometers, right? So, I guess the question is like,